Now we start with the next model. So we consider now distributed source coding. This model, the rate region, was calculated by Slepian and Wolf. So it's a generalization of the model we considered in the first section when we spoke about typical sequences. But here now, instead of one encoder, we have two encoders. So we have a source which emits now two sequences xn and yn. And now we have two encoders. Encoder 1 maps xn into 2nr1 indexes w1, and encoder 2 maps yn into 2nr2 indexes w2. A decoder receives now the sequences w1 and w2 and produces the sequence, the estimate of the sequences x hat of n, w1 and w2, and y hat of n, w1, w2, where x hat I is in x and yi hat is in y for all I. Now we don't consider some rate distortion, we just consider the error probability, like we did in the first model, which we considered where we have a source which only emits one sequences and we have only one encoder. So the problem is now to find the set of rate pairs R1, R2, for which one can, for sufficiently large n, design encoders and a decoder so that the error probability PE can be made arbitrary small positive number. So you see in the model, in the normal source coding model, we have just one sequence x hat n, which was the estimate of the decoder, and here we have only one sequence here. What is the difference now? The two encoders don't work together. So if we have here one encoder, it's in principle, it would be the same problem if they can talk to each other. And then we know what is the result. Let's see on the next page where we'll look at this. So what is the application first of this? We can model this by the following scenario. We have two sensors, the encoders, that observe dependent measurement streams, yn and xn. And they must sense these to a fusion center, the decoder. And the sensor usually have limited energy to transmit their data. So they're interested in communicating both efficiently and reliable. And the obvious strategy for both is first to compress their streams. Then we know what we have before in the first two lectures, that we can compress it to h of x and h of y, and then send it over the channel. But what I already told you, it could be if the two encoders work together, then of course we can assume h of xy. So that R1 plus R2 is greater or equal h of xy if the encoders cooperate. But it's not clear if this is possible. But we will see that surprisingly, also if the two encoders work not together, we can achieve this. And this problem was solved by Slepian and Wolf in 1973. And they found this a surprising result that the sum rate is equal h of xy. And this is approachable. Moreover, the encoding technique involves a simple and effective trick similar to hashing. It's called binning. And this trick has since been applied to many other communication problems. You will see we will apply it to other models also. And we will look now at this trick. So the Slepian-Wolf trick is widely known as binning. So let's look at the result and at the figure again. So I present here you the functional dependence graph of the channel. You see here, we will have to do this for every model we have. You see as a source produce, for example, if you look at a sequence of length 3, produce the pairs x1, y1, x2, y2, x3, y3. And then x1 goes here to encoder 1, x2 goes here to encoder 1, and x3 goes to encoder 1. And y1 goes to encoder 2, y2 goes to encoder 2, and y3 goes to encoder 2. So, and encoder 1 compresses sequence of length 3 to W1, to this index W1, and encoder 2 compress this sequence of length 3 to W2. But now we have only one encoder which receive W1 and W2. So depending on W1 and on W2, he have to reconstruct and make estimates of the first sequence, x1, x2, x3, and of the second sequence, y1, y2, y3. This is a so-called functional dependence graph, and we will write it as FDG for the distributed source coding problem. Now, the result, I already mentioned it, the result will be that we can achieve the following rate. We can achieve all rate pairs R1, R2 in such a way that R1 is greater equal the entropy of X conditional on Y. The R2 is greater equal the entropy of Y conditional on X. And the sum of R1 plus R2 is greater equal than the entropy of the joint distribution of X and Y.